Hi, everyone. You need to see these new images from the Hubble Space Telescope taken on December 12th and again on December 27th, showing the interstellar object known as 3I Atlas. And despite all the data we now have, we still don't know what this object truly is. In fact, with every new observation, the mystery seems to deepen rather than fade. On paper, this story should already be finished. 3I Atlas passed the Sun months ago. It survived the heat. It survived the gravitational stress. It is now moving outbound, drifting back toward the cold silence of interstellar space. By every standard rule of comet physics, it should be fading. Its activity should be tapering off. It should be quiet. It should be unremarkable. But that isn't what just happened. Earlier today, NASA quietly updated the orbital solution file. No press release, no announcement, just a revised data set uploaded to the server, and buried inside those numbers is something that cannot be ignored. When you run the update, the conclusion is unavoidable. 3I Atlas is not settling down. It is becoming more active, not in a subtle way, not as noise, but in a way that tells us the previous prediction failed. This object has changed again. And what matters is not just that it changed, but how it changed. The latest Hubble images reveal something genuinely unusual. They show two distinct jets of material emerging from the object, including a dominant sunward-facing jet, an anti-tail, that is roughly 10 times longer than it is wide. That alone is extraordinary. This is not how interstellar visitors are supposed to behave. Let's slow this down and walk through what Hubble actually saw. The telescope captured long exposure images, about 170 seconds each, using extremely sensitive instrumentation. When astronomers processed these images with specialized filters designed to isolate faint structures, two narrow, well-defined jets became visible. One is strong and sharply focused, pointing directly toward the sun. The second is weaker and extends in a different direction, more consistent with what we would normally expect from a comet tail shaped by solar radiation. What makes this especially important is that the relative brightness of these two jets changed between December 12th and December 27th. That tells us something fundamental is happening at the source. This is not static debris. This is active evolution. To understand why that matters, we need to talk about wobbling jets. A change in jet brightness over time strongly suggests motion. Either the jets themselves are shifting, or the regions producing them are rotating into and out of view. In other words, this object is spinning, and its rotation axis is not aligned with the direction of the jets. As the object rotates, a fixed active region on its surface sweeps through space, causing the jet to slowly change its apparent direction and intensity. When we compare images taken days or weeks apart, like these December 12th and December 27th frames, we can begin to track that rotation. This is critical because we cannot see the surface of 3I Atlas directly. It is hidden beneath a dense dust veil. Jets are one of the only tools we have to infer what is happening beneath that shroud. What's striking is that this wobbling behavior isn't new. When 3I Atlas was first observed back in July, before it reached perihelion, astronomers already noticed a long, narrow jet pointing toward the sun. Even then, it showed subtle changes in orientation, suggesting the source was fixed near one of the object's rotational poles. So now the question becomes unavoidable. What exactly is producing these two jets? There are two main possibilities. The first is that the jets originate from opposite sides of the object. In this scenario, one jet is active on the sunward hemisphere, while the other comes from the opposite side. After perihelion, heat absorbed on the day side could have conducted inward and reactivated material on the night side. As the object passed the sun, the geometry flipped, changing which jet appears sunward and which appears trailing. The second possibility is that both jets originate from the same general region but consist of different materials. The dominant sunward jet could be composed of large, heavy dust particles that resist solar radiation pressure and remain tightly collimated. The weaker jet could consist of finer dust or gas that is more easily swept backward by the solar wind, giving it a very different appearance. Distinguishing between these explanations will require spectroscopic data and precise velocity measurements, which astronomers are still waiting for. Now here's where things escalate. While imaging teams were analyzing these jets, orbit specialists were looking at the numbers, and the numbers didn't behave. Think of the orbit solver as a prediction engine. Observatories around the world feed it precise positional measurements. The solver applies gravity from the Sun, Jupiter, Earth, and the rest of the solar system, then projects where the object should be next. Normally, there are residuals, tiny, random errors. That randomness means the model is working, but in this update, the residuals didn't scatter. They aligned. Every new measurement fell on the same side of the predicted path. That tells us something crucial. The comet is not where gravity alone says it should be. To make the math work, scientists had to update the non-gravitational parameters, the thrust produced by outgassing. Comets are not passive objects. When gas vents from the surface, the nucleus recoils like a weak rocket engine. Until now, that thrust appeared stable. It no longer is. Compared to just 48 hours earlier, 3I Atlas is experiencing a stronger sideways acceleration. This does not mean it's heading toward Earth. There is no danger. But physically, it means a new force has come online. The comet pushed itself off course. And the images explain why. When astronomers blinked deep stack images from one day to the next, the change became clear. The inner coma, once symmetrical, is now lopsided. The brightness peak has shifted. One side of the coma is thicker and denser. The opposite side is thinner and stretched. It looks as if something grabbed the comet's atmosphere and pulled. And then there's something else. When the contrast is pushed just enough, a faint ghostly streamer appears, a new thread of material peeling away at an odd angle. It wasn't there before, now it is. That streamer is the physical source of the sideways push. A new jet has activated on one side of the nucleus. Material is being expelled asymmetrically, distorting the coma and producing recoil. The math and the morphology agree. And then there's the third line of evidence, the light curve. For days, the brightness pattern was stable, one strong peak, one weaker peak, a single dominant vent controlling most of the activity. That pattern just broke. The main peak shifted in phase. The secondary peak surged in strength. Instead of a strong, weak pattern, we now see two peaks of comparable intensity, two flashes per rotation. That means a second major vent has come online. This object no longer has one dominant exhaust source. It has two, operating at similar strength, competing for pressure and momentum. So why is this happening now, after the comet has already passed the sun? The answer is slow physics. When 3I Atlas passed perihelion, the surface reacted immediately. But heat conducts inward slowly, centimeter by centimeter, through rock, dust, and ice. While the surface has cooled, that thermal pulse has continued migrating inward. Now it has reached deeper layers. Down there are volatile reservoirs, carbon monoxide, deeply buried water ice, materials that have remained frozen for millions of years. When heat finally reaches them, sublimation begins suddenly. Pressure builds. Eventually, it finds a weakness. A crack opens. A sealed vent blows out. The internal plumbing of the comet is reorganizing itself. Old vents are fading. New ones are activating. This object is not just changing behavior, it is changing structure. And that's where the risk lies. Each new jet alters the torque on the nucleus. It changes the spin rate. It redistributes stress across a body that is already fragile, a loosely bound aggregate of rock and ice. NASA's language is careful. Updated solution. Evolving morphology. But the physical reality is clear. 3I Atlas is reacting to a delayed fuse ignited months ago. Will this new double-jet configuration stabilize? Will the forces balance out as the object continues outbound? Or will the competing stresses overwhelm the structure? Yesterday, the system looked predictable. Today, the orbit leaned, the coma warped, and the light curve doubled. The story didn't end, it turned a page, and now we're all waiting to see what comes next. Keep watching. In Cosmo we trust.